Hey, well, wonderful. Well, I'm glad to be the last person to have your attention before you escape for dinner and beer and whatever else you have in your future. This paper is about welfare and bunching. It's joint with Greg and with John Mansfield. Uh, I was John Mansfield's advisor. Greg was my advisor. So there's a very strong intergenerational structure of the authorship group here, which will closely resemble the intergenerational structure of the data.
That makes me
And
very old because that means Jonathan is my
he's your grandson. Yeah,
grandkid.
your grandkid has a job. Uh, Needless to say, these are not going to be the views of the Department of Justice. I don't even know if these are my co-authors' views, but they're my views. So this is take it with a grain of salt. This paper, like I say, we're sort of doing two things. There's going to be an application here, and the application is basically about if you give welfare payments to parents, is that helpful for their kids? If so, how helpful? Could it even be harmful to their kids? So we're going to have an application about that. And then the other thing is we're going to have a methodological contribution, which, surprise, involves bunching. Okay, so welfare programs, when you think about why do welfare programs exist, obviously one key reason why welfare programs exist is because poor people need the money. But there are other rationales for welfare programs, and one rationale which you sometimes hear is that if you give money to people who have kids, that might be helpful to the kids. The sort of story behind that is that you give money to parents, and either the parents are directly investing it in the kids, and that pays off some benefits because you're buying like better childcare arrangements, tutoring, get into a better school district, something like that. Or it's sort of reducing the stress level in the house. There's also a story about why welfare payments to parents might be bad for kids, which is the sort of family welfare culture's story, where if your kids observe that you're drawing welfare and you're relying on welfare, then the kids learn that there is a smaller incentive to work than they might have otherwise believed. And therefore, that may increase kids' dependence on welfare. So that is a concern that people have. And lastly, you might have the view that maybe this just doesn't matter that much because maybe when you give money to people, they buy a couch, and the couch has relatively little impact on their kids' human capital development. So the various stories you can tell about what the effect might be. There's a large literature about short-run effects of welfare programs on things like standardized test scores, which is a large literature which is mixed between very large effects and precise zero effects. There is a smaller literature on long-run effects, and the literature on long-run effects is mixed, as I've given some examples up there of positive effects. It's great for kids, or it has no effect on kids, or it's bad for kids. So there's a mixture of these results. I don't know why we get this mix of results. Maybe they're internal validity problems with papers. I don't know. Maybe they're external validity problems with papers. Each of these papers is identifying the effect only for a particular program in a particular context. And if you're a policymaker trying to make a decision about, well, what's going to happen if I implement this new welfare program going forward, that welfare program isn't going to be any of the programs which were studied in any of the contexts which were studied. It's not going to be exactly the same thing. And so what we would really like is some general statement about, like, is welfare in general, as a rule, is that good for kids or bad for kids? So what we're going to try to do in this paper is study the effects of welfare, broadly speaking, total payments to kids on the human capital of recipients' children. And so our treatment variable is going to be the total dollar value of all welfare payments that your parents receive throughout your entire childhood, ages 0 through 18. Broadest measure of welfare that we could come up with. And we're going to have various outcomes which are going to try to capture something about the kids' human capital. We're going to measure their income when they're in their late 20s, early 30s, educational attainment, whether they have a job, whether they are receiving welfare benefits, and what kind of work they're doing. Are they working in a higher or lower skilled occupation? Yeah.
Confused by traditional welfare payments of all sources. Are you talking about Section 8 housing? Are you talking about SNAP? Are you talking about EITC? Are you talking about...
So yeah, so the sources that we're going to have are basically like temporary assistance for needy families, that type of stuff. That's one component. Another component is going to be like food stamps, and another component is going to be like disability payments. Those are the three central things that are going into our number.
very different from the state too, right?
Yes.
It's just clarifying.
Yeah.
Sorry.
Yeah. It's going to vary by, yeah, the eligibility rules are going to vary by year, by state, et cetera. But we're just going to add up the total amounts of money that you're getting, and that's our measure of treatment. Okay. All right, what's the endogeneity problem here? The endogeneity problem, the reason why we would not just like to compare people who receive, whose parents receive more money to people whose parents receive less money is that generally if your parents are receiving welfare, it's probably because your parents have low socioeconomic status at that point in time. And kids tend to resemble their parents. So if the parents have low socioeconomic status, your best guess about the kids is that they're going to have low socioeconomic status regardless of whether welfare does anything or not. And so that's going to make it so that if you don't address endogeneity, it's going to look like welfare is really bad for kids' outcomes. So what we're going to do is we're going to have our method for trying to adjust for this, which is going to combine two features of the data. The first is the familiar thing, which is that there is bunching in the treatment at $0. You can't receive fewer than $0 of payments, and an awful lot of people get $0, something on the order of half the people in our data receive exactly $0 of welfare. And then the other thing that we're going to use is the availability of what we're going to call placebo outcomes. And I'm going to use the term placebo outcomes. It's not exactly how you would use a placebo outcome in other contexts, but I'm using that phrasing intentionally because I want to evoke the ideal variable to play this role is the sort of thing which you would use as an outcome variable in a placebo test. Specifically, it should satisfy a couple of criteria. The first is that it should not, in fact, be affected by treatment. It should be something which is predetermined. And the other thing is that it should be something which, as they say about a good placebo outcome, it has like U comparability. It represents the same sorts of unobservables or the same sources of confounding that you're fundamentally concerned about in your main analysis. So an ideal placebo outcome is going to be something which is affected by the same confounders which are screwing up if I just looked at the basic relationship between welfare payments and how the kids wind up doing. And because our concern about confounding is that first degree relatives have correlated socioeconomic status, we're going to basically choose as our primary placebo outcomes. We're going to look at just a different first degree relative whose outcomes were realized before the welfare payments happened. We're going to look, instead of the children of welfare recipients, we're going to look at the parents of welfare recipients and say, well, I know that the welfare receipt that the parents had in 1990 doesn't affect how well the grandparents were doing in 1979. Okay, this combination of things is going to give us an estimator, which ultimately is going to look a lot like a diff and diff, except it's going to have a rescaling factor thrown into it. And the rescaling factor is going to get identified using bunching. I'll mention at the end, you can also motivate this in terms of a latent variables model. You can connect it with the latent variables models of the sort like Viviane had in her talk and Greg was talking about earlier, et cetera. All right, preview of results. The overall effect is kind of small or mixed. There's not, I wouldn't say it's a slam dunk case that welfare either improves or hurts human capital. I would say there's evidence pointing in both directions. There's some evidence that, yeah, like investments maybe go up, educational attainment might be going up somewhat in response to welfare payments. On the other hand, like the family welfare culture story, there's kind of some evidence for that too. It's not super strong evidence. Lots of stuff is not statistically significant, but if you just look at the point estimates, it's trending in that direction. Nonetheless, my overall takeaway is I wouldn't expect welfare to have completely transformative effects one way or the other. That's again, my views. You can ask Greg for his synthesis later. So our data, we're going to take data from NLSY 79 and CNLSY. So I'm going to use kids, parents, and grandparents to refer to the three generations here. The parents are the people receiving welfare payments. The grandparents are the parents of recipients. The kids are the kids of the recipients. So we have this three-generation structure. And the grandparents, everything that we see about them, we're going to see about them in 1979. And then the kids are going to be born later and receive welfare later. For the kids, we're measuring their outcomes ages 26 to 31. Just to give you a flavor of what things look like, about half of the people in the sample are receiving welfare. And then if you say, like, how much are people getting from these different sources? So this is like your cash payments based on disadvantage. There's your food stamps. and then this is your sort of disability payments and things like that. And what you can see is that generally, like if you're getting food stamps, there's an 80% chance that you're in one of these other programs too. So these programs tend to occur in the same set of people, and there are various people who've argued that like even in-kind benefits are pretty fungible with cash. Oh, that's the total amount received throughout the entirety of childhood. So this is like from 0 to 18, I'm getting like 50,000 bucks, conditional on receiving welfare. On average, I'm getting 50,000 bucks. Here's the beautiful graph of bunching in this particular context. So you can see here again that about half of the sample receives exactly 0 welfare throughout childhood, and then we get a bunch of other people past that. And as usual for a bunching and treatment thing, the key thing here is that the bunching at 0 creates this discontinuity and selection bias. Think about the sort of families who receive $0 in welfare as opposed to the people who receive just barely positive. Some of the people who receive $0 of welfare, they just barely didn't get welfare payments. Like if you had just changed their socioeconomic status a tiny little bit, they would have been getting food stamps. So some of those people are comparable to the people who are just barely positive, but some of those other people are corporate lawyers and dermatologists and stuff like that, where you would have to change their socioeconomic status by quite a bit to make them be eligible for welfare. And so therefore, not surprisingly, if we look at the observed characteristics seem to be distinctly discontinuous at 0. The people who receive 0 welfare, the mothers have higher AFQT scores. The grandfather works in an occupation which has higher log mean earnings. The grandfather has higher educational attainment. The grandmother has higher educational attainment. Really, any variable you look at has this clear pattern of a jump in selection bias if it's at all correlated with welfare receipt. So this lovely jump in selection bias is presumably not accompanied by a jump in treatment effect. Presumably, if the government gives you 50 cents or gives your mom 50 cents, or if your mom finds 50 cents under the couch, that's probably not going to have an important, quantitatively large effect on your life course. And so therefore, we're going to assume that treatment effects are pretty small of receiving just barely positive. So therefore, obviously, we're going to see discontinuities in the outcomes because there's selection bias, but these discontinuities in the outcomes are presumably solely attributable to selection bias. It's just the reason why log earnings of the kids jump between if your parents got $0 versus $1. Presumably, the reason why there's a jump there is just that the sort of kids whose parents got $1 were going to have worse outcomes anyhow than the sort of kids whose parents got $0. Okay, so that's all selection bias. And in fact, again, the size of the discontinuity is exactly the selection bias when you make what I'm going to call the near comparison. The near comparison I'm going to use to refer to comparing people who get 0 versus just barely positive. Okay, so we know how much selection bias there is in the near comparison. Obviously, we don't really care about knowing how much selection bias there is in the near comparison per se. What we care about is like measuring the how much selection bias there is when I compare like the 50,000s to the 0s. Because then when I know that selection bias, I can correct for it and get treatment effects. And the question is, how are we going to convert our knowledge of selection bias in the near comparison into knowledge of selection bias in the far comparison? How are we going to do that? Well, again, sort of similar to the intuition behind like the Caetano-Nielsen paper, you sort of might think, well, boy, it seems like if you got a lot of selection bias here, if there's a big discontinuity here, it kind of seems like there's a lot of endogeneity, and maybe if there was a small discontinuity here, maybe it seems like there's not as much endogeneity. I don't know, but exactly how do you convert the size of this jump into a guess about how much selection bias there is in these more distant comparisons? And here's the way we're going to approach it. The way we're going to approach it is to just talk about how many times more bias is there in the far comparison than in the near comparison. We want to make a statement like, when I compare the 50s to the 0s, there's like twice as much selection bias as when I compare the just barely positives to the 0s. If I can make a statement like that, I'm done. Because I know how much bias there is when I compare the 0s to the just barely positives. I know, like in log earnings, The jump goes from like 9.9 down to 9.7 or something. So there's a jump of about 0.2. So there's selection bias of 0.2. So if there's twice as much selection bias when I compare the 50s to the zeros, then when I compare the 50s to the zeros, there's selection bias of 0.2 times 2 is 0.4. So then I just adjust for that and I know the treatment effect. Okay? So that's our basic approach, is we're going to think about figuring out how many times more bias there is, and how are we going to guess how many times more bias there is? Well, I don't know. We have all these we have all these characteristics of people. Let's look at some of these characteristics. Let's look at grandfather's educational attainment. Well, if I compare the just barely positives to the zeros, there's a gap of about 1. And if I compare the 50s to the zeros, there's a gap of about 2. It seems like maybe there's about twice as much selection on this variable. Let's come over here and look at the grandmother's educational attainment. If I look, locally, there's a gap of maybe, I don't know, 0.7 or so. And if I look to 50 to 0, it's a gap of about 1.5. Seems like about twice as much selection once again. And if you look at each of these measures, you're going to get a number which is pretty similar to 2. No matter which of the measures of socioeconomic status you look at, it looks like there's about twice as much bias in the far comparison as there is in the near comparison. And so that's going to be our assumption, is that if all the observables are telling us that there's twice as much selection in that far comparison as there is in the near comparison, our assumption is going to be, yeah, seems like there's about twice as much selection. Okay? So, yeah.
You could just as easily,
but you could just as easily say how much selection would there have to be for there to be a 0 result. That would have been another way of characterizing what you're doing.
Yes. Yeah, you can totally do it that way, exactly. You can talk about a ratio, you could talk about the ratio which is required to get a 0 result as well, and you can comment on the plausibility of that, totally. Yep, exactly. Yep. Okay, so that's our basic approach, and you'll notice that what we've done here is we've sort of, relative to the CCN type approaches, there's no latent variables model here. There's no like latent treatment that we had to assume. We didn't have to make a distributional assumption, anything like that. So we sort of got around doing that. And in order to get around doing that, we have to believe that we have these observed characteristics, which are sort of informative about the relative bias in different comparisons. So we need to have observables which are reasonably rich, even if they're not rich enough to bias selection on observables. Okay. So here's the econometrics of it. So our object of interest, I'm going to call ATT of W. So W is going to be our variable for welfare. So we're going to ask, what is the average treatment effect of receiving little w dollars as opposed to 0 among people who actually receive little w dollars? Okay. I'm going to use 0 plus to refer to just barely positive amounts of welfare receipt. You can think of it as the limit from the right. As you approach 0. And so our first key assumption, like I say, is going to be that the treatment effect goes to 0 as you fall to $0 of welfare receipt. So that is, again, should be a familiar assumption from the stuff that was talked about earlier today. And again, like I say, the same decomposition Greg was talking about, you observe a difference in outcomes between the people just barely positive and at 0. That difference in outcomes, it's got to be the sum of a treatment effect and selection bias. And once we assume that the treatment effect is 0, then for that local comparison, it's all selection bias. Okay, I'm going to skip over this because I already talked about that. Here's a little bit more notation. I'm going to let...
Sorry. Can you go back to the... I don't understand your assumption. Can you go back? Under assumption 1, the difference in Y, can you explain this to me? I'm missing something. The difference.
Oh, this is yeah.
You're saying that the discontinuity in the outcomes is equal to the selection bias in that comparison. You just mean to say that the only thing that happens there is selection bias, and therefore, okay, that's it.
Exactly.
I thought you were making a proportionality assumption or something.
No. Okay. This is literally just commenting on assumption 1 means that the discontinuity in Y tells us the selection bias in the near comparison. Then here's a little bit more notation. So I'm going to refer to difference in variables between people with like one amount of welfare versus another. I'm going to refer to that using deltas. And so for any generic variable z, I mean, there's no actual variable named z, but just generically, if there were a variable named z, I'm going to use delta z of w to refer to the difference in the average of z when I compare the people at welfare equal to little w to the people with welfare equal to 0. Okay? So for example, a way to represent the selection bias in my FAR comparison, when I compare the people, let's say, with 50,000 to people with 0, is to write the difference in Y zeros between the people at 50,000 versus the people at 0. Okay, so that's the selection bias. That is the thing which we would like to adjust for. If I know how much selection bias there is in the comparison, then I'm done. I can just adjust for that. And then next, I'm going to let Y tilde be our placebo outcome, whatever our placebo outcome is, and we're going to have different choices of placebo outcomes. But so here's our assumption, is if the FAR comparison has twice as much difference on Y tilde as the near comparison does, then there is twice as much selection bias in the FAR comparison as in the near comparison. Okay, so this is the ratio. This is the ratio of how much difference is there in the placebo outcome in the FAR comparison relative to near. And this is the ratio of how much selection bias is there in the FAR versus the near. And this assumption.
David, sorry to interrupt.
Yeah.
So because the Y tilde is a placebo, Y tilde is equal to Y tilde of 0. Am I right?
Exactly.
Exactly.
Yep.
So what you're saying, what you're doing is a proportionality across outcomes.
Yeah. Yep. Proportionality of potential outcomes between potential Y tilde and potential Y is another equivalent.
They're all proportional to the placebo, and then, okay.
Yeah,
so
exactly. Great. And so now I'm just going to add in assumption 1. So first of all, this thing is already observed. We see the placebo outcome. We see how different it is between the 50,000s versus the zeros. We see how different it is between the just barely positives and the zeros. So these things are already observed. This is the thing we want to get. And then this last thing right here, what's the jump in Y0 right at the discontinuity? Under assumption 1, the jump in Y0 is just the jump in Y. Like, Y doesn't deviate from Y0 because there's no treatment effect is getting $1. Okay, so under assumption 1, now we have an equation with only one unknown left over here. All the other things are identified, so we can back out what the selection bias is. And then, and so here is our way of getting the ATT. So to get the ATT, we take whatever the difference in outcomes is, and then we subtract off how much of it is selection bias. Okay, and so the selection bias term there, I've just taken that last equation and I've rearranged the terms. I've done what you would do to solve for selection bias. And I want to point out, I've written it in a particular form here. What we're taking is the difference in means for Y. How different is Y between the 50,000s and the zeros? And we've subtracted off how different was Y tilde between the 50,000s and Y zeros, except we've rescaled Y tilde by the ratio of the discontinuity in Y to the discontinuity in Y tilde. Yep.
Can I just ask a quick question? So I understand that the welfare that the kids get or the parents get doesn't affect the grandparents. That part I understand. But the interesting part to me, and I wanted to ask you to help me understand that, is the selection that makes my kids 30 years later get the welfare is a function of unobservables that are present back in the generation of the grandparents. So there's something about the selection mechanism that you need to assume some sort of stationarity or some timing variant, latent variables to justify assumption 2. What's the intuition there? Can you help me understand?
So a way to think about it is that, so again, it doesn't have to be that the latent traits have the same manifestation in each possible generation. It doesn't even have to be that the strength of the correlation in latent traits between parents and kids remains the same. It's really more of a shape restriction that however strong that is, like the gap that jumps between the zeros and the 0 pluses is half as big as the gap that emerges between the zeros and the 50s. So we allow, functionally, this structure allows for the sorts of things where like there isn't complete stationarity in this process between the kids and the parents. And the stuff where it isn't stationary, that's going to show up in the rescaling factor here. In the discontinuity in Y tilde might be smaller than the discontinuity in Y because maybe the grandparents had a weaker relationship with the parent stuff than the parents do with the kids. The question is just like, did it get weakened just as much at the discontinuity as it got weakened away from the discontinuity? So if it got like weakened to like 30% as much bias at the discontinuity, but only half as much bias away from the discontinuity, that would screw with our assumption. But if you weaken it by 60% everywhere, then that's fine. Does that make sense? Okay, yeah. So I want to just point out that this looks a lot like a difference in difference estimator. So think about, one way to think about a diff and diff is to say, you could just start off saying, ignore the pre-period, just look right now. I'm going to compare the treated group to the control group. I see there's a difference in outcomes. And I could claim, oh, great, I have a causal effect. And I'm going to do a placebo test to show you that I have a causal effect. I'm going to look at the pre-period and see the treatment group and the control group are exactly the same. Oh, shit, they're not the same. They have a difference in their outcomes. Okay, I'll just adjust for the difference that was there before. Okay, that's what a diff and diff is. You take the difference in today's outcomes between the treated and controls, and you subtract off the difference in your placebo outcomes, like outcomes that occurred before the treatment started. So that's a diff and diff sort of in our notation, except that in our case, we're going to say, well, sometimes our y tildes are a different variable from y. Sometimes our y tildes are attenuated in some way, whatever. And so we're going to allow a rescaling factor where we say, you know what, you should really take that violation you picked up in the placebo test. You should really take that violation and scale it up a little bit to get the right amount of selection bias adjustment. And again, that rescaling factor is going to come from, does y have a larger discontinuity than y tilde? Okay. So, okay. Thinking about this assumption, I want to point out the obvious, which is that this assumption is probably not literally true. This assumption is an approximation of reality. It's sort of in the flavor of, I personally think of common trends assumptions this way, that common trends assumptions are usually not literally true, but you hope that they're close enough to being true that it's reasonable and you get informative estimates. So what are the circumstances under which the estimates that we get this way are going to be close enough to being true that your estimates are going to be qualitatively informative? If you think of having a linear model, suppose that you think like the structural equation for y is like a bunch of characteristics, linear, additively separable. One thing which would make this assumption be true is if every confounder, every placebo outcome that you could pick demonstrates the same ratio. If every variable I look at has twice as much bias when I look at the 50s to the zeros versus the just barely positive to the zeros, and I got a linear model, great. There's going to be exactly twice as much selection bias in that FAR comparison. That's one possibility. The other possibility is that maybe you pick a placebo outcome which really captures the same mix of stuff. So some of the confounders, there's a ratio of 3 to 1. Some of the confounders, there's a ratio of 2 to 1. But like, it just so happens that the mix of confounders which go into your placebo outcome looks like the mix of confounders which goes into your main outcome. In that case, you're also fine. So I think, you know, in terms of implementing this, condition number one is probably the first thing you should look for. If you're thinking about doing this and your observed confounders have radically different ratios from each other, you might not want to try implementing this method. But if stuff looks very similar to each other, then this seems like it might be a reasonable method. Again, the thing about the placebo outcome involving the same mix of confounders, again, this is sort of choose your placebo outcome to have what we, you know, again, what people call U comparability. You can also relax this and sort of think about like, okay, you know, I can claim I know exactly what the ratio is, or I can claim that I know kind of some range. You know, if all the ratios are between 2 to 1 and 2.5 to 1, it seems kind of unlikely that the actual ratio is 17 to 1. So you might be a little bit more agnostic about it and say that, you know, if I'm trying to get a flavor about what the effect is, it's probably not too far away from the range of the stuff that I see.
David?
Yeah.
Could you rewrite some of the methods that we saw earlier today in your notation in the thoughts that your scaling factor is something like taking the placebo of the upper tail?
The placebo of the upper tail.
So the other methods, like one of them is the symmetric tail.
Yeah.
Right? So that seems to me similar in terms of what you're doing. You're just giving me other data. They're using the tail. You're using some other data.
Yeah.
Okay, but could you rewrite those conditions to look like your conditions so I can compare them better?
Here's what I'll say. I'll talk about this at the end of my talk. Maybe, I don't know if this answer is going to answer quite your question because I'm not positive I understand exactly what you're asking, but you can use this if you're implementing the other design. You can also implement this design with it. as an additional approach where you dispense with the distributional assumptions. And in that case, the scenario where you want to dispense with the distributional assumptions, as I'll talk about, is like if you have an observed characteristic which appears to be linear in latent treatment, then the assumption 2 will be satisfied, and you don't need the distributional assumption.
I want to rewrite their distributional assumption using rescaling.
So. Exactly, yeah. So precisely, so you can do that. Precisely, you can do that. Okay, all right. So next, I want to just talk about what if there isn't nonlinearity. So suppose that, for example, in our situation, I've said there's twice as much discrepancy on socioeconomic status, but you might think twice as much difference on socioeconomic status might not translate into twice as much confounding because maybe confounding isn't linear in socioeconomic status. So in particular, like you have models, let's say with borrowing constraints, where like if you give somebody $1 and they're already above their borrowing constraint, that's not going to make that much of a difference. But if you give them $1 and they're below their borrowing constraint, boy, that makes a big difference because that's going to go into investment. So, so it's perfectly plausible that you might have nonlinearity here. But thankfully, if you have nonlinearity, which again would screw up assumption 2 and leave you with assumption 1 as the only assumption you believe, nonetheless, you can still comment on what's happening with treatment effects because the deviation that's due to nonlinearity is exactly equal to the bias that we're going to get in our estimates, okay? So for example, if you sort of take our results to say that we find no effect on things, but you don't believe assumption 2, then you should recast our results to say, seems like welfare gets rid of whatever effects of whatever nonlinear effects there are of socioeconomic status. So it's sufficient to get rid of that, doesn't do anything more than that. If you believe that, if you're thinking about policy implications, you know, that would imply that cutting welfare might hurt people. If you got rid of the welfare system, that would be bad for people. But on the other hand, if it exactly gets rid of nonlinearities, that kind of seems like maybe the marginal dollar is not going to help that much. You've already gotten rid of all the sort of Becker-Tomes related pathologies that you wanted to get rid of with the welfare system. So increasing welfare might not improve child outcomes, even though decreasing welfare payments relative to the world as it existed in the 1980s and 90s might be bad. Okay, here are results. Here's what we get for our various outcomes. So these are effects per $1,000 of welfare. This is sort of averaging across different ATTs for different amounts. I haven't put stars on anything. I assume even though it's the end of a long day, you're still capable of multiplying standard errors by 2. So you can see here that, you know, earnings, the point estimate's slightly negative. As I'll show you, there are, you know, choices of placebo outcomes you can have where you get a positive point estimate for that. The quality of the occupation that people work in seems to be going up. So they seem to be working in occupations maybe where there's a higher education and earnings requirement, not statistically significant effects, but the point estimates are positive. Point estimate for educational attainment is positive, not quite statistically significant. How much you want to read into it? You choose your own adventure. And then probability of not having a job and probability of being on welfare, those seem to be going up at the same time. So, you know, if I'm just looking at the sign and not worrying about significance, I would say that it looks like maybe there are some more investments that people are winding up more skilled, but then maybe there's some increase in family welfare cultures at the same time. Or, of course, you could look at all of this and just say it seems like there's not much of anything happening, which would be a perfectly plausible interpretation as well. Here is a way to visually represent what our design looks like. So what you can think of is, again, we're sort of taking the placebo as a way of producing a counterfactual. We're using the placebos to produce a counterfactual, and the way you got to do it is you say, okay, I take my placebos and I rescale them so that they fit exactly with the discontinuity in Y. I take my graph, I shrink the vertical axis until and shift it around until I exactly overlap with the discontinuity that I had before. And now I'm going to overlay what this graph looks like for my placebos. That's what's in the dashed line here. And so the deviation, that's the Y0, the target that I'm going to hit if I have no treatment effect. And so what you can see here is small amounts of welfare. The point estimate is that actually these guys' earnings are coming in lower than you would have expected if there was no welfare. And then as you get over here, the point estimate goes above. But again, obviously, nothing here is statistically different from 0. Here's what it looks like, for example, for average occupational earnings. So you can see for average occupational earnings, there's maybe more of a pattern where it looks like as if I'm thinking about where did that treatment effect come from, where I showed you a positive but not significant relationship here. Well, the positive estimate's primarily coming from the people who have very large amounts of welfare receipt rather than the people who have small amounts of welfare receipt. Okay. Here are specification curves to show you what the results look like with every possible choice of placebo outcome combined with every possible choice of welfare, quantity of welfare that you might be receiving. So again, this is ordered from the smallest effect per $1,000 to the largest estimated effect per $1,000. And what you can see here is that it doesn't really matter that much which placebo outcome you throw at it. You're going to get qualitatively similar results, which is that the effect on log earnings seems pretty close to zero. Okay. Here's the effect on not having a job. So you can see there's some placebos where you can pick where you get a statistically significant effect on having no job. You can't find anything where there's a negative effect, but you can certainly find plenty of specifications where there is not a statistically significant effect. Probability of being on welfare at all, again, by and large, you're getting positive estimates. A few of them are statistically significant. And again, they're all within roughly a comparable range. Here are effects on educational attainment here. Once again, you get a bunch of them where it's statistically significant and positive. They're pretty much all positive across different specification choices, but lots of them are not significant. Here's average education in your occupation. Here is log of average occupational earnings. Again, sort of similar stories where stuff tends to have the same sign no matter which placebo I'm picking. But, significance varies, and the point estimate is it's not literally identical across different choices. Okay. I'll just briefly mention falsification tests to do for this. We can also sort of ask whether welfare receipt affects test scores. Welfare receipt at older ages affects test scores at younger ages. And for most combinations that you can come up with for welfare amounts and placebo effects, most of those are finding a zero effect. Some of them you find a statistically significant effect, which is, again, not surprising because the modeling assumption is not literally true. This slide says conclusions, but you're not allowed to get beer after this because I am going to give you a couple more slides after this. So these are only the empirical conclusions. Only the empirical conclusions, I would say, overall, doesn't seem like payments to parents necessarily or particularly transformative for kids' labor market outcomes. There's some kind of evidence leaning in the direction of maybe there's a little more investment in the kids. Also some evidence leaning maybe in the direction that there might be family welfare cultures. Okay. Now let me talk about why this design is not just main course, it's also side dish. If you do some of the other approaches that have been talked about, this is a useful thing to do in combination with another approach. So in particular, the two most common approaches which people have done with bunching and treatment. One is I'm going to run a bunch of regressions. I'm going to use Carroll's test to figure out which of those regressions suffer from endogeneity. And then some of those I get a fail to reject. And then we do the thing which we were not supposed to do in your statistics class, and we turn that fail to reject into an accept. And we say, great, this model might be right now because I failed to reject it, okay? And the obvious issue that you have with that is, well, fail to reject doesn't necessarily mean that the thing is right. And so we have to ask, were we going to reject the thing if selection on observables was actually false? Or is there some chance we would have failed to reject? And so what we want to comment on using this placebo bunching design, what we can comment on if you're doing that sort of, I'm going to run OLS and test it, we can comment on, was this actually a precise fail to reject or was this an imprecise fail to reject? Okay, that's thing number one. And if you're going to do like the CCN latent variables model where you got that distributional assumption, you got the linearity assumption, what we're going to be able to help with is say, well, suppose you're having a hard time worrying about, is my distributional assumption reasonable or not? What can I do about that? Again, this is going to be a way to just get rid of the distributional assumption while maintaining your sort of broad framework. So let me talk a little bit more about the selection on observables designs. My personal way of thinking about Carroll's test is that when you assume continuity of treatment effects. Again, you know exactly how much selection bias there is when we compare 0 to just barely positive. And we use that information to test a model because a model implies an amount of selection bias in that comparison. Like when you run OLS, the difference in outcomes between the just barely positives and the zeros gets decomposed into coefficient on treatment times the gap in treatment, and the gap in the controls times the coefficient on controls. Okay, so the X prime betas, where X's are the covariates, not treatment here. So the X prime betas, how much the X prime beta jumps is your regression model's guess about how much selection bias jumped, how much selection bias there was in that comparison, okay? So what Carroll's test is asking, as I think of it, is, was that jump in X prime betas, is the endogeneity that your model thought was there, is the selection bias that your model thought was there equal to the selection bias which you, through the grace of bunching, happen to know was actually present in that comparison, okay? And we're basically testing whether the jump in observables, therefore, is equal to the jump in the outcome. And you could have a very precise fail to reject. You could say, I find that the observables jump by 99% as much as the outcome does, and it's only plus or minus 2%. Great, wonderful. That's a very precise fail to reject. I know that at least looking locally, I asked whether this could account for the selection bias, and boy, does it do a great job of accounting for selection bias. But if instead you fail to reject because, well, the observable jump was 70% as large as the jump in Y, plus or minus 50%, then you would say, I have no idea whether selection on observables holds or not. It could be the case that selection on observables holds. It could also be the case that, like, my observables only actually accounted for 20% of the selection bias locally just looking at 0. So what can we do? What kind of sensitivity analysis can we do to think about, if I'm in the world of a slightly imprecise fail to reject, how much could that screw up my estimates? How sensitive might my estimates be to selection on observables not exactly holding? So this is how you use it, and I developed this a little bit more in a paper with Hector Ormeño. So a way that you can adopt this placebo bunching thing is to just set your Y tilde, maybe it's hard to, the tilde got mushed in with the parentheses there, but that's, take your placebo outcome to be the index of observables, okay? If selection on observables holds, then whatever differences there are in Y0 in a comparison is equal to the difference in X prime beta. Therefore, assumption 2 holds. The relative jump in the observed characteristics equals the relative jump in Y0 because they're the same thing. However, it can also be the case that assumption 2 in our paper holds even if selection on observables doesn't hold. Here is the scenario where that is the case, is if my observables got rid of 70% of the selection bias in that near comparison, and they also got rid of 70% of bias in the far comparison, and they've got rid of 50% of bias in each of the comparisons, in which case I say, oh boy, I needed twice as much bias correction locally, and I also needed twice as much bias correction globally. Okay? So this is a way of translating that uncertainty, because when you do the placebo bunching approach with this method, you're going to get additional uncertainty about your estimate, which incorporates the fact that, like, yeah, I don't actually know whether this accounted for all of the jump or not. Okay? So this is a way of doing a sensitivity analysis around that. The other sense in which our method plays well with other children is that it goes well with CCN designs, as we already talked about, which is that suppose we're going to have this CCN assumption that the potential outcome is linear in latent treatment. Okay, we're just going to keep that assumption. We're just going to get rid of the distributional assumption. We're going to replace the distributional assumption by the idea that there's some variable that we found. Doesn't even have to be like a great placebo variable. It's just a variable that's linear in latent treatment. If you got any variable that is linear in latent treatment, then this thing plus that thing together guarantee our shape restriction that we need in assumption 2 is going to hold. So All you got to do if you're doing a CCN thing is look around in your index in your set of covariates and find something which looks linear over the positive range. You probably should have such a covariate. If you're arguing that like your potential outcomes are linear in latent treatment, there should probably be something that looks linear in latent treatment, or at least linear in treatment over the positive range. So if you're doing a CCN approach, I think you should probably try doing this. You should probably try doing this in addition to other stuff as just an alternative version. You may believe your distributional assumptions, but this is just an alternative thing that you can throw in and make sure that you get intelligible results, sort of consistent with whatever else you're getting. So that's my last slide. It doesn't even say conclusions on it, but I'll take your questions.
Any questions?
David, so this approach relies on the fact that you have something to learn about an outcome for which there is confounding from an outcome for which there is no treatment effect.
Yes.
Right. So the idea here is that the outcome on the grandparents is informative about the selection of the outcome of the parents, let's just say.
Yep.
Am I right? Why don't you just control for the outcome of the grandparents?
Yes. So why not just control for the placebo outcome? So this is coming back to what I just talked about here with selection on observables designs, is you could say, I'm going to let my y tilde be, maybe I'm just going to control for one placebo outcome. Then if I did that, it would just be, that placebo outcome times its linear coefficient or something like that. Then again, one possibility is that if you do that, great. Maybe selection on observables holds, that's wonderful, and then assumption 2 holds. But maybe selection on observables doesn't hold, maybe controlling for that particular measure of socioeconomic status doesn't really dent endogeneity that much. But if it has a representative pattern that there's twice as much bias in the far comparison as in the near comparison, if that's true for other confounders too, then assumption 2 can still hold true. So if it were fine to just control for the thing, great, our method works. But also, if it's not fine to just control for the thing, our method has a chance of working too.
There's a technical aspect too that we show Monte Carlo related to that, is that if you use y tilde as a control, that is a noisy measure of what we actually want to control for. So this goes back to Chamberlain 94, where we talk about, and actually it goes back to my job market paper, the proxy IV issue, is that whenever you add something that has noise, it may solve the main endogeneity problem, but it does introduce a new one. And that the approach here avoids introducing that new one.
I think this also relates to Miles Kimball's question this morning, where functionally you can think of all our placebo outcomes here as being a noisy proxy for socioeconomic status. So why is it that just adding our controls doesn't solve endogeneity? I didn't show you guys, but there's still a discontinuity if you control for the stuff here. So it seems like probably selection on observables doesn't work in this case. Why might that be the case? Well, because every one of these variables is a noisy proxy for socioeconomic status. So the coefficients on them get attenuated. Therefore, you fail to account fully for endogeneity. Yeah.
Yeah, quick question. In the last second to last slide, would be the case that maybe that's not the one.
This one?
Yeah, this one.
Yeah.
Would it be the case that assumption 2 hold if everything in your model belongs to a class of multivariate Gaussian distributions? Because every conditional mean is linear. It doesn't need to be, selection on observables. You can the linear projections are all going to be linear, but the coefficients are going to be projections, not the causal effect. But it feels like the ratio would be constant.
Yeah.
So
if I'm in a model where literally everything
look
is
at that,
linear
like
in
that is also always true if Y0 and W star they're jointly Gaussian, and that's also always true if W tilde and W star is jointly Gaussian.
Yeah.
Like that's always true. Like
Yeah.
if you say one is normal, the other one is normal, they're jointly normal, it has to be true. The conditional functions are linear. So it's interesting because it's one of the cases that it looks like you had omitted variable bias, but the structure of the system is such that any linear projection is not going to give you the causal effect. But together with the logic of the bunching, you're able to figure out the size from that bunching discontinuity and bring it back to what you want to adjust. And if you look at the way that you wrote the DID thing, it looks a lot like the conditional mean of a bunch of normals. I mean, it's just, I don't know. That's exactly what you do if you try to start from the conditional mean of delta y of w after observing another thing is correlated with it, delta y tilde of w, and the regression coefficient is that ratio there to identify.
Yes. Yeah. Yeah, yes. So exactly. So that is an example of a well-behaved scenario where all our dreams come true and our assumptions hold. So I hope for many applications where that is true. I think one of the strengths of this though is that things can be weird. I think Greg mentioned earlier, and I never paid off his comment, that the direction of selection as you go from 0 to just barely positive doesn't have to be the same as the direction of selection as you move away from that, right? It could be, we allow for the possibility that maybe after it jumps down, maybe all these placebo outcomes go back up again or something like that. So we allow for a lot of weird cases here, but absolutely like nicely well-behaved cases are often going to satisfy our assumptions. Yeah.
Okay, I think we're out of time. Thank you.
Cool.